question about the homework.
Uh-huh.
For the Wiley homework, well, I had a couple.
Uh-huh.
I had a question for number 14. Do you want me to read the question?
Yes. Go ahead.
Okay. So this one is about a trombone can produce pitches ranging from 85 hertz to 660 hertz approximately. When the trombone is producing a 464 hertz tone, what is the wavelength of the tone in the air standard conditions?
Mm-hmm.
So yeah, I don't.
All right, so that first statement, this right here is just some trivia for you to know, right? Mm-hmm. And then this right here is our known value. That's a frequency, right?
Mm-hmm.
Okay, so quick issue of preference here. Did you guys read the chapter?
Yes.
This would be in chapter 9. Mm-hmm. And do you guys have page numbers in the electronic version of the book?
Yes.
Okay, so if we're looking at page 251, they give you an equation there, and that's what you need.
Okay.
And then we need another piece of information.
Did you say 255?
The page is 251. I'm trying to look up what they use for standard conditions really quick here. So one of the key factors that we need to know, and I hope you guys got this from your chapter, but I'm not quite sure how well they emphasize it, is your standard conditions basically is referring to the weather. Your speed of sound can change according to what the density of the air is, and that has to do with the temperature and things like that. So we normally, if we do any sort of question that has to do with the speed of sound, we have to assume what the speed of sound exactly is, because that does vary according to what things are going on. So that number is always a little bit different. And you guys should have had a statement in your chapter that said what we would assume for standard temperature and like standard speed of sound. But I don't actually see it in the book. So I will show you guys how to do it. And then you just need to consult your book to get the exact number that they want to use.
Okay.
And then we're going to use the equation on page 251. And this is another thing. So in your book, it says this. Now, the problem is this letter right here is a Greek letter nu, and it's basically indistinguishable from a V in most people's minds. Like, I certainly can't write it in any way that you can say, oh, that's a V, that's a nu and not a V. So the way you normally see this equation is V equals, and they usually put the F first, F lambda. I find this easier to remember and easier to connect to the variables we're using, but I don't want to confuse anyone by using a different equation than the book uses. So this thing on this side, both of these, this stands for speed and this stands for velocity. It's the same thing. Lambda, we're using both. Lambda is your wavelength. And then F stands for frequency, and I like that because that's easier to remember than try to look at that and say nu. It stands for frequency when we already know that we have a velocity in the same equation. I find that really confusing. So do you guys have a preference whether it helps you to go along with the same equation that's in the book, or whether you would like to use the more standard equation? Does anyone like the red one better? Does anyone like the blue one better? Any thoughts? I'm just going to use V equals F lambda, but just be aware. They're the same equation. And your book also in equation 9.2.1 writes it out in words. So if all else fails, just get the words and follow those. Okay. But for me to do it here, I'm doing it in front of you. I'm not going to be writing out all those words. So we're going to use V for velocity, F for frequency, and lambda for wavelength. Okay, so our known here is 464 hertz. And what is the unknown, the question that they're asking us to solve for?
The wavelength.
Okay, so then our unknown is our lambda. What is lambda? And that's going to be in units of meters. Wavelength is actually literally a length. So we know frequency. And then the thing is you guys need to look up in your book what exact number they want you to use for standard conditions for velocity of speed of sound. I'm going to use 440 meters a second. That is one valid speed of sound. You guys will actually need to look up and see what exactly. Let's actually solve this symbolically first. That helps anyway. Also because all of you will be given slightly different numbers for this anyway when you go into your homework. It will not use the same numbers over and over again. So let's solve this symbolically anyway. So I suspect if you're stuck with the whole idea that you have to look up V. Is that where you guys are having trouble?
Yeah.
Yeah. Your book will give you that, and it will be a number kind of close to the one we're using. So we'll just solve this right here algebraically. Lambda equals V over F. And then we use the F that they give us right up here. And I would say 440 for V, but it just depends on exactly what and your book will give you a number for that. And then you just divide.
Okay.
Does that make sense?
Yes.
And if you guys happen to find it really quick in the book, otherwise I will scan the book when the meeting is over and I will put it. Has everyone seen the equation sheet that's linked to on the Canvas page?
Yes. And I found it in the book and it says it's about 331.
Okay. So it's 331. And I'm going to go ahead and put that in your equation sheet with the constants down below where your constants should be. And do you have a page number or a reference number on that? Does it say 9 point something?
Yeah, it says, like, mine says page 252, and it has, like, in bold, speed of sound and air, it's about 331 meters per second.
Okay. Yeah, and I might have, the number I had in my head might have been a little bit off. And that's the other thing is the speed of sound in different media, different objects, like the speed of sound in stone or the speed of sound underwater or whatever, they're all different. So that'll always be a number that you probably need to look up. Okay. So I'm adding that right now to our equation, our constants. So if you had a question on the test or something, you should be able to use like this one page for everything that you would need. If we were having the test in the classroom, this is what you would have with you. So I've updated that. We would just plug it in. We would do the calculation and we would come out with just a number. So what kind of number are we going to get, guys? Bigger than 1, less than 1, close to 10, close to 100. You guys can see the whiteboard still, right?
Yeah.
Okay, so what kind of number did we get? This is, a second. Okay, and then the other thing is what units did we get? So units of frequency are hertz, right? That's actually 1 over seconds. So if we have meters per second divided by something per second, what units did we get? This is going to be in units of meters. And if we plug it in, we're going to get a number less than 1, right? 0.7, 0.8, something like that in there. Did anybody do the calculation? It's 0.71. Oops. 0.71 meters. And then, like I said, everyone's going to be given slightly different given numbers, so this will not be exactly what you get. But knowing that this comes out of a trombone, does 0.71, a trombone is kind of coiled up, right? Does 0.71 meters fit realistically with the geometry of a trombone? Yeah, right. You could imagine that the pipe of a trombone fits the geometry of the wave. And that's why, you know, something like a brass instrument, the reason why low notes come out of big instruments is because physically the wave has to fit the instrument. And long wavelengths correspond to low notes. A flute is the smallest and makes the highest notes because physically the wave fits it. Okay, does that make sense to everyone? Does anyone have any more questions on that?
No, I think I got it.
Okay, great. Anything else?
I had a question over 19. It says, I'll put it in the chat box because it's
okay. Let me see if I can pull up the chat. Different parts of my menu box keep disappearing when I use things like screen sharing. So there it is. I'm seeing some stuff. Okay. All right, so this is the one you guys only had to read like 2 or 3 pages of chapter 4, right? This is a chapter 4 problem.
okay.
And can you guys see the chat box on my screen share? Or is it just the whiteboard?
It's just the whiteboard.
I tried to expand that. But... Okay, so the question is, how high above the Earth's surface would you have to be before your weight would only be 0.3 times its current value? And that's 0.300, so we have 3 significant figures. So the Earth's radius is 6,378 kilometers. All right, so what do we know? And I'm going to give you guys a little bit longer to think and to answer so we can, it's not just me trying to shove things down your throat, but you guys can have a chance to think about this. So looking back, if you guys did everyone read their chapter 4, those couple pages that I put in the learning experiences?
Yes, I did.
Okay, so that would be like page 109 and right around there.
So are you using the gravitational force equation with this one?
So universal gravitation. F equals a whole bunch of stuff, right?
Yes.
G times M1 times M2 over R squared. So that's a force. Weight is also a force, right?
Yeah.
Weight is what? M times G. So if you compare these two, what are these two masses, M1 and M2? If it's your weight standing on planet Earth, what are the two masses that we're going to be plugging, well, that we would be plugging in? We don't actually have to plug them in to solve this problem.
I think that's where I was confused because I thought you would have to plug those two in.
Okay.
So
well, I'll show you a cute trick here, but what are the masses? The two masses that have something to do with your weight are your own mass, right? And what other mass? So does your weight change if you go to the moon?
Yes.
Or Jupiter or any other place, right? So it depends on the thing that's creating the gravity to give you your weight, right? That thing in our case is the Earth. So one of the masses is you, and one of the masses is the Earth. Let's just make M2 you. So that means this big number right here is actually equal to little g. Since we live on planet Earth, this r would be the radius of the Earth, right? That doesn't change very much. We do know that g, the gravitational constant, does change a bit. This big G is the universal gravitational constant. It doesn't change. So we've got the mass of the Earth, we've got big G, we've got the radius of the Earth. And if we multiplied all of those out, we would discover shorthand that they equal 9.81, or, you know, varies a tiny bit depending on where you are, including elevation. Okay, so these are actually equal to each other. And this thing in this big circle is actually equal to G. So I'm gonna take a few things back here. So what we want to know is what it takes to get a new G equal to 0.3 times your old G. And your old G is all of this stuff here. So I'm going to go ahead. Oh, partly I'm already paged down. Oh, that's inconvenient. Okay, so if you look at everything in this circle, and our total force is this, but your mass doesn't change. So this doesn't change, that doesn't change. But basically, yeah, let's just plug it in though, so you guys can see. Times G times the mass of the Earth over R squared. But the only thing that's changing is R. So you want to know what happens to R to give 0.3. So 0.3 times R old squared is G times M1 over R new squared. And we're just calculating R new. Well, if you look, G's on both sides, so that cancels out. M1's on both sides. So you get 0.3 divided by your old R squared equals your new 1 over your new R squared. It's kind of hard to handle numbers that are in the denominator, right? So we're going to be solving for our R new, right? We want to know what our radius is. So if we multiply both sides by R new squared, and we would want to get both sides times our old square too, right? We want that out of the denominator as well. So if we just solve for R new, we get over 0.3 R old squared. And then we would need to take the square root to solve completely for it, right? I'm gonna go ahead, just make this bigger. Since we started halfway down the page for unknown reasons. Give it a little minute to think. Oh, never mind. I thought we could just make our page bigger, but it made everything bigger. So we'll just work over here in a different color. All right, so square root of R new squared equals R new equals square root. And what's the square root of R old squared? That's just going to be our old radius, right? So it's going to be the square root of 1 over 0.3. And they might, I don't know if they're going to give you all the same numbers there or not. So does this agree with what we would expect, right? The further away from Earth you're going to be, the smaller your weight is going to be, right? So does this give an answer that makes sense there? If we said we wanted to know the radius where our weight is the same as it is now, and we plugged into this number right here is the number where what our weight would be, we would get the answer that our weight would be the same as it is now at the radius the same as it is now, right? So that's what we would expect. Our weight would go to 0. Technically never. If you look at this, it would mathematically give you something that doesn't work. You divide by 0. So the smaller the weight is, the further away your radius is. So that's an expression for it. Does that make sense to everyone? The math is a little tricky, but once you see it, hopefully it makes good sense. So if this was hard, like you guys couldn't think through it, you could actually plug in all these numbers here. But that would just involve putting more big numbers in your calculator and you would end up with the same answer at the end. So it's not actually necessary to plug in anything. They do give you this R right here as part of the problem. You would plug that in. Okay, any further questions on that particular question?
What is that symbol in front of the R that you just circled?
That is just, well, this is a square root, this part right here. Yeah. Okay, yeah.
Okay, so it's just the square root of R divided by.
But the square root is only over this. It's not actually taking the square root of your R. It's just taking the square root of that math. The R is outside of the square root now because it started out squared.
Oh, okay.
When it was down here, it was squared. So when we took the square root of both sides to get rid of this square, it got rid of both squares. Okay. I'm about to erase this. Does everyone have all of the processing they need on it?
Yes.
Okay. I just expect someone to yell if it wasn't okay. Here, let's scroll up now. We'll have more space next time. Any other questions? Any spots that you guys were confused with? And does anyone see anything we don't have in our equation sheet that we need? I think I pretty much put everything in there, and I even put a little explanation of the two equations that we use for wave speed. So you guys can use, they're both on that sheet. You guys can use whichever one makes the most sense to you. Has anyone looked at the lab for this week yet?
I haven't.
I have.
So this is bungee jumping, right?
Yeah. Mm-hmm.
This is one where you're going to be graphing, and we have talked about graphing a little bit in these Zoom meetings before. So if you've missed the previous Zoom meeting, you probably want to go back because I actually did do a little demo, and I've got that marked as it'll be linked in the announcements where we've linked our previous Zoom meetings. We did a demo of how to graph in a spreadsheet. It's super, super easy. I don't recommend, we still get a few graphs done by hand, but it's really easy to have trouble with that. It takes a lot of time. It's usually messier and harder to read. So we just really strongly recommend everyone just take a minute. Spreadsheets are intimidating at first, but they're actually quick and easy to learn. So we would recommend that you do the graphing that you need to do in the spreadsheet. And then they basically give you the same lab directions that we would have on campus when we actually do this in person. But they also provide a video and a data file. So instead of actually doing the experimental process and writing down your data, you just are given the data and you need to read through, they give you all the directions of what you would have needed to do in person so you can understand what you were supposed to do. You have to think about that, think about your data, and then you do some data processing, which is basically you use the spreadsheet, you graph it, you need to use the spreadsheet to display the equation. Then you plug into the equation to find out basically what you're doing is you're saying how many rubber bands do you need to safely drop. We usually use some kind of dollar action figure. You make a little bungee cord out of so many rubber bands, and you do it successively, more and more rubber bands, and you see what safe drop level you get for each number of rubber bands. Oops. So they actually tell you in the lab, and I cannot remember right now what they tell you, but if they say graph bands versus drop height, where do you put your bands? You would put your bands here. I'm not saying that's how it is. They actually switch it from what's intuitive to me. So if they say graph something versus something, that's always your Y, whatever is here on the vertical axis, versus your X. So you need to actually read the lab and follow whatever directions they give you there. So it might be bands versus drop height, it might be height versus bands, but one each is on each axis. And it's a linear thing if you graph your data. I'm going to choose a different. So you get a set of data points. For some reason, it's not letting me draw individual dots here. So you ask the computer to draw a straight, perfect line through these. If you were drawing this data by hand, you would have to get out a ruler and you would have to eyeball and see what is the best fit line that goes through all of your data points. And then it turns out in the lab, you have a limitation. The height of the room is as high as you can actually drop a doll. But what we actually do is we go and we throw it off the balcony in the back of the library. So you're given a height, I think it's 5-something meters, total end height that you need. So whichever axis it's on, I think it might actually be the y-axis, but whatever axis is your height, you go to 5 meters. And remember, if you were doing your data by hand, you would need to actually have a scale where each box is a certain number of length, and you would actually have to count out and find the point that's 5 meters. And then you have your best fit line that your computer drew, hopefully, but you would also be able to draw it with a ruler. And that crosses at a point where you could read off whatever number of rubber bands that you would need. So you get that in class. We actually calculate that number. You actually would use the equation that your spreadsheet spits out. You would solve that equation. You would get a solution for your number of bands. Then you would loop those bands together, you would hook them to your doll, and you would go throw it off the balcony in the library and see if your doll survives. It's actually kind of fun sometimes. So that's what just basically understanding wise you need to do. You need to make sure that you read the lab carefully, use the right axis for which variable that you need. Don't necessarily use my diagram here because it may be reversed, but it works the same way. Whatever axis is your height, you find where your 5.1 meters is, or whatever height that they give you is the height that you need to arrange, and you check and find out what number of rubber bands is needed to do that. So the key for this lab really is mostly just to read and understand the directions and to follow them, and to make sure that you do a good job with your graphing. Your graph is quite a bit of your grade. So make sure you do that. And if you don't know your particular spreadsheet formula, how to display, I can tell you it's called a trend line in one of them, or a best fit line. I do show you in Google Sheets how to do that in the little demo. I told you guys you would need it. So I did that a week or 2 ago, and that video is still there. So you guys can all go look at that if you have any trouble with your graphing. And that's the main part of this that's tricky for some students. Conceptually, the lab I don't think is very difficult, but the whole process of using some amount of data that you can measure, like how far you can safely drop it all with rubber bands in the classroom, and then using that to extrapolate something that you can't measure is actually an important skill and something, and it's kind of a fun lab. So hopefully that's good for everyone. Any questions obvious on that? You guys can all, I'm going to go ahead and delete this, but you just need to learn how to get your best fit line and then to use that line to find out what you need to know, which is the number of bands that you need in the end.
I just had one quick question.
Uh-huh.
For the drop height, we're using the average, correct? Drop trial?
So for your the initial process, you drop it multiple times to just get good data.
Mm-hmm.
So yeah, if it says you do 3 trials from multiple numbers of rubber bands or something, then yeah, you take whatever, and they actually give you the data. So then you just need to calculate that. So yeah, your data, if it gives you multiple trials and you just follow whatever directions it gives you in the lab, if it says take the average, then yes, that's the data that you use to make your line is the average of multiple trials at different heights.
Oh, okay.
Which gives you more precise results, especially, you know, when you're standing there on a chair in the classroom trying to drop a doll and measure how far it went. Okay. Any other questions on that? Okay. I also wanted to check, since you guys are the people who are here on Saturday night, I do think we've been getting generally a bigger group if we do it on Sunday morning. But according to the survey that I did, Saturday night was actually better. So I want to check with you guys. Is there anyone who's here now who can't make it Sunday morning, who would want to argue for this time to stay the same? Because I'm wondering if we would get more, you know, actually match up with more people's schedule if we did it Sunday morning again.
I like this time. Last week I just forgot, and your reminder helped me today.
Okay.
But
Yeah,
I can do Sunday mornings also, so it doesn't matter to me.
Yes,
Okay.
Sunday morning is good.
What's that? I couldn't hear quite.
So Sunday morning is good for me. And
Okay.
Saturday.
Any other preferences?
It just kind of depends. My work schedule isn't really set, so sometimes I work Saturdays and sometimes I work Sunday mornings. So
Yeah, the one advantage of Saturdays is if we could do that, it actually sometimes, especially the first week, we had a very long session and it took a long time to video process because the Zoom app has to video process it. And then if I post it to YouTube, YouTube also has to process it separately. So that can take a little bit. So it's kind of nice if we do it Saturday, everyone who's available Sunday morning can still have access.
Yeah.
And you guys also can post questions separately in the question thread. I believe that the same ones that were brought up during the session today were the same ones that were posted. But if somebody couldn't make the meeting, you can still do that and we can discuss it. And you have some hints and some instruction to go by. So I'm thinking Saturdays are still better. According to the survey, Saturdays was still good. But if we find people are struggling to come, if they make comments on I asked the same question on the thread.
For Saturday, what time?
Sundays, I can't remember what option I gave.
Oh,
Like,
on Saturday, what time? When?
oh, well, it will be the same as it was this week. So Saturdays at 4 is our regular time now. We wanted a regular time so people could actually make arrangements if that was necessary, if they wanted to. And so I would really like to keep it consistent, but definitely if there's more people who would find Sunday mornings better, that's an option that we're considering. So feel free to comment and we can try to keep everyone's opinions in mind. But according to the survey, this was the best time. So that's why we landed here.
Thank you.
Yeah, I think perhaps there were a lot of people who forgot last week, so we might just try to keep it, but also open it up for comments if other people really would like to move it. That may be considered also.
We have groups in for physics. We have phone number. Then we have some question. We can
You
other.
guys, yeah, you guys are free to do that. I believe that you can message each other in Canvas, can't you?
Yes.
Okay, so yeah, I'm not going to assign you groups or require anyone to talk to anyone else. We try to do the discussion questions so you guys get a little bit familiar with each other and you feel comfortable. So feel free to try to open channels, and anybody who wants to have a conversation can do that. But we also try to open and really encourage you guys to ask questions on the discussion thread